Alright, welcome to the Unit 3 Problem Solving Part 1 video. Now, it's unusual for me to do a video for the problem solving because normally we're just trying to put together the concepts that you've already looked at up to that point in the unit. However, this is a little bit different because one of the things that the AP exam likes to do is they really like to take the information that you learned so far in this unit and present it to you in a slightly different way from what you would typically do in, say, a textbook. And so I wanted to make sure that I went through an example showing you a very typical way how they would like to do this. And one of those ways is to present to you a graph of a function where that might be the function you're referring to, but it also might actually be the graph of the derivative of some other function. And based on which function you're dealing with, how we can use this graph to interpret the behavior of some other function that we don't necessarily know. So we've got this graph here. The continuous function f, which is what we're showing, is defined on the closed interval from -5 to 5. The graph of f consists of a parabola and two line segments, as shown in the figure above. So again, just to be clear, the graph that they're showing up here is considered the graph of f. Then it says, let g be a function such that g prime of x is equal to f. So right away, they're telling us not only is this the graph of f, but this is also the graph of some derivative g prime for some other function g. So this graph is going to serve two different purposes for us throughout this problem. And this is going to be a multi-part question. So in some parts, we're going to actually be referring to the graph or to the function f. In some other parts, we're going to be referring to the function g. So you do want to make sure that you're aware of which function you're working with because that affects how we are treating this graph. All right, so here are some of the questions that you might be asked. So for part A, fill in the missing entries in the table below to describe the behavior of f prime and f double prime. Indicate positive, negative, or 0. Give reasons for your answers. Okay, so because we're talking about f prime and f double prime, then that means for this particular question, we are interpreting this graph to represent the graph of f. Okay, so from -5 to -2. From -5 to -2, they're asking us about f prime. Now remember, the relationship between f prime and a function is if f prime is positive or negative, that tells us whether the function is increasing, the function f is increasing or decreasing. Well, the difference is this time we already know about the function, so we're just going to try to think in reverse. So from -5 to -2, notice that f is clearly increasing on that interval. And because f is increasing, we know that f prime must be positive. Now it does say to give reasons for your answers. So f prime is positive on the interval -5 to -2 because f is increasing. All right, now from -2 to 0, notice that f now is decreasing, meaning f prime must be negative. So again, f prime is negative on the interval from -2 to 0 because f is decreasing. From 0 to 3, once again, now we can see that from 0 to 3, f is once again increasing, so that means that f prime must be positive. So now we can say f prime is positive on the interval from 0 to 3 because f is increasing. And then finally from 3 to 5, once again it's very clear that f is decreasing on that interval, so we can say that f prime must be negative. So f prime is negative on the interval from 3 to 5 because f is decreasing. Okay, so that takes care of f prime. Now for f double prime, remember the relationship between f double prime and f, the original function f, is that f double prime being positive or negative indicates the concavity of f. So now let's take a look at the concavity. Well, notice from -5 all the way to 0, f is concave down. And since f is concave down on that entire interval from -5 to 0, then that means f double prime is going to have to be negative across that entire interval. So we can say that f double prime is negative on the interval from -5 to 0 because f is concave down. Now here's the tricky one. So from 0 to 3, now notice from 0 to 3 there is no concavity, right? That's just a line segment, so it's not arcing upward or downward. But now let's think about it. So if f is a line segment, then that means f prime would be the constant slope of that line segment, which in this case is 2/3. So the derivative is actually a constant, which means the derivative of that, remember the derivative of a constant, is always 0. So that means the second derivative must be 0. Again, if the original function was a straight line, was a line segment, then that means its derivative must be a constant, which means the derivative of that, so the second derivative, must be 0. So we can say that f double prime is 0 on the interval from 0 to 3 because f has no concavity. And then finally, from 3 to 5, we actually have the same story, don't we? From 3 to 5, f is once again a line segment, so that means f double prime must be 0 because, again, f is a line segment, so that means its first derivative would be a constant, so its second derivative would be the derivative of a constant, which is 0. So again, we can say the same thing for f double prime on the interval from 3 to 5. And looking at what I did earlier, I suppose you actually could have said the same thing from just 0 to 5. I take that back now that I've said that, because notice we do have that cusp or corner point right there. So we don't want to actually include 3 in any of our intervals here when we're talking about f double prime being 0, because f double prime would actually be undefined there. So because f has no concavity. Okay. So again, that's how we can use the graph of the original function to think about what the values of its first and second derivative would be based on the behavior of f. Okay, now there is no value of x in the open interval -1 to 3 at which f prime of x equals f of 3 minus f of -1 over 3 minus -1. Explain why this does not violate the mean value theorem. Now, just to make sure you understand what that means, remember all of these theorems you've learned. What these theorems are telling you is, as long as the conditions for the theorem are met, then the conclusion of the theorem has to be true. It has to. So what's happening in this example, or in this part, is they're saying that there is no value of x, or as we've called it, c. There is no value of x or c in the open interval -1 to 3 for which f prime equals the slope of the secant line. They're telling you that it doesn't exist, and they're trying to ask you how come this does not go against what the mean value theorem guarantees. In other words, if we're trying to prove that something isn't going against a theorem, It's because the situation we're looking at doesn't actually meet one or more of the conditions for that theorem. The only way that a theorem can seem to be contradicted is if the conditions weren't met in the first place. So the question we have to ask ourselves then is, why does the mean value theorem not apply to this particular function on this particular interval? Now, if we're talking about the interval from -1 to 3, then that means we're looking at all of this right here. So between -1 and 3, we're looking right here. Well, remember the two conditions for the mean value theorem. First, f does have to be continuous on the closed interval from -1 to 3. Well, clearly, f is continuous on that interval. There are no holes in the graph. There are no vertical asymptotes. There's no jump in the graph, so this is a continuous function. However, the second condition, remember, f has to be differentiable on the open interval from -1 to 3. And if you notice again right here, at x equals 0, we do have a corner point or a cusp. And if you recall, a corner point or a cusp is a location where we know that the function is not differentiable. So we can say, since f is not differentiable at x equals 0, and we can say there is a cusp there. Remember the difference between a corner point and a cusp. A cusp is formed by curves as opposed to a corner point, which would be formed by two line segments. So for example, this point here, that would have been a corner point, but we're not talking about that one. Okay, so there is a cusp there. So since f is not differentiable at x equals 0, f is not differentiable on the open interval -1 to 3. Therefore, the MVT doesn't apply. So that's why the fact that there is no x in the open interval doesn't violate the mean value theorem, because the mean value theorem doesn't apply. All right, moving on to part C. So now this time, it says find all values of x in the open interval from -5 to 5 at which the graph of g has a point of inflection. Explain your reasoning. Now, because we're now talking about the graph of g, then remember that means we don't want to think of this graph over here as the graph of f. We want to think of this as the graph of g prime. Okay, so now, if I'm looking for a point of inflection, remember that is a point at which the concavity of the original function g changes. So if I want to know, and so I'm just going to kind of write down my thoughts here. This isn't quite the response yet. I just want you to see the thought process here. So remember, g has a point of inflection when concavity changes. But remember, concavity changes when either g double prime changes signs or g prime goes from increasing to decreasing or decreasing to increasing. So that's the thought process here. So there are two different ways we might determine where we have a point of inflection. But because we're looking at the graph of g prime, it would make much more sense for us to look for this behavior. We want to see, where does g prime change from increasing to decreasing or decreasing to increasing? In other words, we're looking for relative extrema of g prime to determine where g changes concavity. Okay, so if I look at my graph, clearly, g prime does change from increasing to decreasing right up here when x is negative 2. The graph of g prime changes from decreasing to increasing here at x equals 0. And once again, g prime changes from increasing to decreasing at x equals 3. So that means g has a point of inflection at x equals negative 2, x equals 0, and x equals 3, because g prime changes from increasing to decreasing, or vice versa, at those locations. And that's all you would need to say. Okay, now, before I go on, I have a feeling some of you are a little bit tied up because you're thinking about those corner points or cusps, and you're thinking, wait, how is that a point of inflection if it's not changing concavity? This is the biggest mistake that students will oftentimes run into, is misinterpreting what we're trying to think about. Remember, we are discussing the concavity changing or the point of inflection for g. G is some function whose graph we don't even know. This, what you're looking at here, this is the graph of the derivative of g. Okay, so what you have to try to separate for yourself is, as soon as you recognize that the graph you're looking at is the graph of the derivative, you cannot describe the same behavior of the derivative graph as the graph of its original function. So in other words, clearly g prime is increasing from negative 5 to negative 2. That doesn't mean that g is increasing from negative 5 to negative 2. Or g prime is clearly concave down from negative 5 to 0. That does not mean that g is concave down from negative 5 to 0. You have to use the relationship that we know between g prime and g in order to determine the behavior of g. So work really hard to separate which function you're working with. Okay, one last part. All right, so the final question says, at what value of x does g attain its absolute maximum on the closed interval negative 5 to 5? Now notice, remember, this is the graph of g prime. And because g prime is defined everywhere, remember that that does mean that g must be continuous everywhere. So in other words, we know that g is continuous on the closed interval negative 5 to 5. Again, remember, differentiability implies continuity. All right, so because we know g is continuous on the closed interval from negative 5 to 5, then remember that means by the extreme value theorem, there must be an absolute maximum and minimum on the closed interval from negative 5 to 5. And if you recall from what you've done so far in this unit, those absolute extrema have to occur either at an endpoint or at a critical number. Now notice, remember, critical numbers are where the derivative is either equal to 0 or undefined. This is the derivative. G prime equals 0 when the graph of g prime hits the x-axis. So that means the only time g prime is equal to 0 is actually at these endpoints, negative 5 and 5. So that means we have no critical numbers between negative 5 and 5. So that means the absolute maximum and the absolute minimum have to occur at the endpoints here. But now, which one's which? Now here's where you have to try to remember once again. This is g prime. And notice that because the entire graph of g prime lies above the x-axis, that means g prime is positive on that entire interval from -5 to 5. And remember, if g prime is positive on that whole interval, then that implies that g is increasing on that interval from -5 to 5. So think about what that's saying then. If we know that g is increasing the entire time, then that means on whatever graph of g we have, so at -5, I have no idea what the y-coordinate of g of -5 is. I have no idea what that is. But whatever it is, from -5 to 5, oh, that is very messy. Sorry about that. We know that g has to be increasing the whole time. I don't know exactly what it looks like along the way, but I know it's increasing the whole time. And if that's the case, hopefully you can clearly see that the maximum, the absolute maximum of this graph must occur at x equals 5. So therefore, the absolute max is attained at x equals 5. Now notice I'm only giving the x-coordinate because notice in the directions it says at what value of x. And you're going to find that to be the case often, where they're really just asking you for the x-coordinate. Please make sure you pay close attention to that, because if it doesn't ask you for more than the x, you don't want to try to spend any time trying to find it. In many cases, such as this one, you can't find it. And in some cases, you might have the actual information you would need to find it, but finding it would take a lot more time than you need to if you're not asked to. Okay, so this was an example of how you might encounter the information that we've been learning in this unit, how we can use the first derivative and the second derivative to help us interpret the behavior of a function. Or what if you're actually given the graph of the derivative of a function? How can we use the graph of the derivative to interpret the behavior of the original function? Okay, good luck.